Hi everyone, welcome to Field Ecology Habitat Analysis of Prairie habitat sampling that we did. So I pulled down the Google spreadsheet that you guys had filled in and made this a CSV file. I named it prar.hab.22 and basically I think I just added samples. So 1 through 36, looks like we had 36 samples and everybody got their data in. So we're going to use this file. This CSV file should be saved in a folder on your computer or on Dropbox. Make sure that you are saving everything to the cloud later on so that in case you lose something or something happens to your computer, you can always do it later. But everything does have to be in a folder. So for example, you might want it in Field Ecology with a subfolder Habitat Sampling Data Analysis or something like that. So here we go. So for this week, instead of having you guys worry about typing in code from a sheet or a lab handout, I am throwing out the lab handout this time. I redid the code for you and I'm going to give you the code file. So you should also have your RStudio code file. Here I have a lot of things up because I'm working on different things, but basically we have Radar Hill Assessment Field Ecology 2022 .R. So all R scripts have to be saved with the .R at the end. So you can open this up. So if you have it in your folder, just open it, click on it from your folder, and it will open in your RStudio. On here, I have some identification type information at top so that we know what it is. It reminds me what I'm doing if I only come to it every year. But basically, this is, again, BIOS 3760. This is our Field Ecology Habitat Lab for Prairie Restoration. This lab was originally done in conjunction with Dr. Rebecca Snell's PBio, Restoration Ecology. And so we shared some of the codes, but I've actually adapted it just for this class. So that's what we're going to work on today. So first thing that we do is we need to load libraries. Now, remember, every time you open up RStudio, you need to load the libraries. If you've never installed a library before, you need to do that for the first time. So we can either do it by going to Packages, Install. My mouse has been weird, but you could type in dplyr and then hit install that way. Another way to do it is with code. So I'm going to come down here and type install.packages, and then I would write in quotes dplyr and then run it. Now, why I would do it down here instead of up top is because this is not code I need to run again. Once I install that code, I never need to put it back in, or the library, I don't have to put it back in unless I update, that kind of thing. So a couple ways of doing it. You're welcome to put it up here. What you could do is put install libraries, run for the first time, and put in your install packages and have them there, but then skip down to your load libraries. Now, I'm going to go ahead and delete that because I don't need to do this. Another thing I want you to get in the habit of, I showed some of you this last week. So notice a lot of times I'll put 4 hashtags before and 4 hashtags afterwards. And that actually allows us to index. So if I come down here, it has an index basically, and I can say set working directories, that kind of stuff. Okay, so that will kind of help you go from thing to thing a little bit quicker. So go ahead and run and load all your libraries. You can come up here and hit run. I am lazy and I like, if I'm on a PC, it's Control Enter. If I'm on a Mac, I think it's Command Enter. So you can go ahead and just do that. As long as your cursor is on the line, it will run those. So these are all libraries that we're going to use today. Then what's really important is that you always set your working directory. Now there's a couple ways to do this, and you can look up on the internet. You can actually type in the path name for everything. You can also go to Session, Set Working Directory, choose the directory, and then you can kind of just scroll to wherever that's going to be. Okay, I'm not going to do that here because I already have it. If you do this, then what I would do is come down here and copy and paste the code. So my working directory, this is one thing that you will actually have to change. So you will need to set your own path for your working directory and go ahead and run it. Okay, then what we're going to do is we're going to read in our CSV. So again, I don't know why I named it PRAR. I was trying to make it be short. So Prairie, HAB 22 CSV. Another good convention, we're not going to follow it the rest of the time today, but most of the time it's a good idea to put _dat. So we're going to read in this file, the CSV file, and I'm going to actually tell R to call it Prairie _HAB _22 _dat. So it's a really handy thing. Anytime you have a data set, have _dat at the end of it, and it can help you actually search for things. So here I'm going to go ahead and run this code. If you don't have this, then you can go ahead and come up here, import data set from text file, browse. If you've already set your working directory, it will be in here. You can click it and open. Okay. You can also go ahead and copy and paste the path here after you do click. So I'm going to move that and get to cancel. And again, my cursor mouse is being really weird. Okay, so we can always type capital view Prairie HAB 22 data, and we can actually pull it up. So here we can actually see everything. Couple other handy things. Again, if my working directory was a little bit emptier, it would be easier. We can come over here and see that this Prairie HAB 22 DAT has 36 observations of 46 variables. That's always a really good thing to check to make sure R imported it the way you thought it should. So we do have 36 observations. We took 12 samples for each group, 4 groups, 36 samples. And the variables are the species names, so we can always check on that. Now, a lot of times we're going to want to make 2 different separate data sets for some of our analyses. So we're going to practice that here. So I have some text here that you can read. But biggest thing is that when we look at this data set, we're going to make what's called an environmental data set with all the species information or the information about our samples, like the metadata, okay, about our sites or in samples, and then we're going to make it another data set with just the species. So if we come back over here and when we looked at view, maybe I just do that instead of clicking on it since my cursor isn't working. We can come up here and I can hover over these. So this is column 1. I come over here to mean LAI. So everything over here up until mean LAI are metadata, information that describes our samples. So we know that columns 1 through 10 are going to be metadata that we want to put out in our environmental data set. And then we also know that the rest of them are going to be in our species. And we can do that here. So this is, again, column 11. We could scroll through and over, but we can also see that it's 46. So we want to have 11 through 46 in the other. So here I have a hashtag make the environmental or plot data. So we're going to call this RH for radar hill _ENV, environmental data. And what are we doing? We're telling R that we want to make this new object called RH environmental out of the Prairie Habitat data set. So we're going to use this data set. We want all of the rows. So remember again, if there's nothing before the comma, that says that we want all of the rows. And after the comma, 1:10, that says that we want to keep columns 1 through 10. So we can run that. And instead, you can do names or whatever, but you can also do head, and you can see what it looks like. And we always should double check to make sure that R is doing what we think it's supposed to be doing. So we can see that we start out with observer column, and our last column is mean LAI. We can also come up over here and note that we have 36 observations of 10 variables, and that, again, is correct. We had 36 samples, and we wanted 10 variables this time. Now we're going to just make the species data set. So here it's going to be radar hill _ species, again abbreviated. And again, we already double checked that we want columns 11 to 46. You should always check this. This may not be the same with your data set. If you're doing this fall of 2022, it is correct. But other years you might have to actually check in and see if it's the right numbers for you. So we'll make this data set. We'll do a head to check it. We can see that we get our first species. So that's a good thing to check. Is that the first species that we expected? And then it says there's 6 by 36, but it can't show us all of them. So it kind of shows us some of them down here. We can come up over here. It's RHSP. So again, 36 observations of 36 variables. And again, that's what we expected. We had 46. 46 minus 10 is 36. So we should have had all 36. We can also check just by running names. Oops. I didn't have it all in there. So RH _ SP. All right, and then these are all of the names of our variables or our species that we have in there. So again, this would always be a good idea to double check that that is correct and that we have all of the data that we expected to have. Okay, we can also check that row names and sites and column names or species, that kind of thing. So row names, there aren't going to be really row names, but it does do, oops. Again, my cursor. All right, 1 through 36, we have 36 samples. We can check names. We already did that. I'm not going to do it now. We can also look at the structure that all are numeric. So here, these are all species, 1 for present, 0 for absent. So it should be read as a numeric value, and that is what we want R to read it as. So we confirm that that is the case. If we look at structure of RH environmental, same thing. Now we get each of our variables. Observer is a character. Date is listed as a character this time. Time's a character. Sample is a number. Quadrat's a number. Habitat is a character. And we can see we have in, out, that kind of thing. So this is always a good thing to double check ahead of time just to make sure that R is reading it the way we expect it to. All right, we can also check to see how many levels of factor we have. So last week, some of you had 3, like blue, lowercase blue, uppercase yellow, and lowercase yellow, and that ended up being as 3 levels. So we always want to make sure that, you know, Excel might say yellow is yellow, but in R, any differences in spacing or capitalization is different. So because habitat is a character, we have to say, tell R we want to use the function levels, but we want to tell R that, you know, if this is a factor of RH environmental habitat, okay? So we can double check that, and we do see indeed we have in, not, and out, okay? So 3 levels, which we expected. If you have a lowercase o or something else, if you have some NAs or something like that, you should go into your original data set now and fix it before moving forward. Okay, so now what we're going to do is pull some summary data, okay? But first, we are going to actually indicate what species are like native prairie species or quality prairie species. And so we're going to make a vector, and we're going to call it Prairie. So this vector is an object, Prairie, and we're going to put these names in this, okay? So again, if you wanted to add more, you would just kind of go in there, do names, and then copy and paste it so that you could put whatever species you wanted in there. When we run this, remember we're making an object called Prairie, but when we run it, we don't actually see anything unless you type it. So if you actually come down here into the console or in your code, whichever one you want, I'm going to type Prairie and see what we get. So we do indeed get what we told it to. Okay, so Prairie is an object that we made. It's a vector of these species names. We could do the same thing with invasive species. We're not going to use this in this lab, but for example, if you wanted to put together a list of non-native or invasive species, you could add them here, call them an object called invasive, and then run it. Here, Rosa multiflora or multiflora rose is a non-native invasive. Okay, now we need to remind ourselves what our data look like because we want to do a couple things. So first, what we want to do is we want to find out how many species are in each sample. So that would be species richness. Species richness is the total number of species observed. So we want species richness per sample. To do that, we have to do a little bit of data wrangling. There's several ways you could do this. You could do it simply in Excel and sum the columns. But here we're going to actually use some code from dplyr, the library, and pull it together. So we're going to make a new object or a new data set called RH underscore species number. So this is radar hill species number. Okay. We're going to add row names called sample. Okay, so this is just some code I've added in here so that we can put things together. We say add row names to what? RHSP is our data set. Okay, we're making a new variable called sample, and we want it to be an integer. That's what those first two lines do. If we actually run, you can always do this to see what you're looking at. So I'm just highlighting that part of code, and then I can see it. So the first two lines of code, this is all it's doing. It's adding sample 1 through 36 to each of these lines here. Okay, now the next line of code, we're going to tell it that we want to gather some information, okay? But we don't want to include, we want to count how many species are present in each sample, okay? So the key is going to call species. We're going to make a new variable called species, and we want to know whether or not they're present or not. So ones are present, 0 for absent, right? We want to tell our what columns in this do we want to call. We don't want to call sample, okay? But we want to call it just in the species that we have. So here we're going to tell it in columns 2 through 37 of this thing, because there's 37 columns. We want it to count how many species are present. Then we're going to tell it to group by sample and summarize. And we're going to make a thing called total SP. So total SP are the total species. And the formula for that is equals sum present. So if they're present, sum them, okay? And then put it in the column called total species. And then we want to actually put this data back with the environmental data set so that we can analyze it later. So there's a couple ways we could do this, but one of the easiest way is by left joining. So basically we can take one data set and left join it or join it with another data set. You can also use right join. And we want to tell R that we want to put them together by sample number. Okay, so left join the environmental data set that has all of our metadata in it. We need to join it by sample. So I'm going to go ahead and run all of this code. I'm going to run ahead, and now we can see. So we can check. We have sample 1 through 36, the total number of species per sample. Okay. We can also look over here on RH species number. We still have 36 samples, and we now have 11 variables. So we added to it. Instead of 10 variables, now we have 11 variables to this. We can check out our second column. So this looks like it's correct. It's actually counting the number of species that are present. But maybe we want to know what's the minimum maximum range. So again, if we do summary of the data set name or object name, $ variable name, and we actually get minimum, median, mean, and maximum. So we have between 1 and 8 species present in each of our samples. The average is 3.667. Okay, now we're going to do the same thing, but we're going to do the number of prairie species this time. Okay, so we're going to call this new thing, new object called RH prairie number. So same code as above with a few different changes. So again, we're going to add rows to RH species. We're going to add a row or a column called sample. We're going to mutate it, okay, make it be as an integer. Again, we're going to gather rows or columns 2 through 37, and we want to know whether the species are present or not, group by sample. This time we want to filter the species that are prairie species, okay? So this piping, percent in percent pipes, the species that are prairie species that we identified above. Then we're going to summarize, we're going to make a new variable called Prairie SP, and that's going to be summing of those present ones, and then join it, okay? So I'm going to run that. I'm going to make a header, and now we see that we have prairie species. It looks like 10021, that kind of stuff. So we can again check and do a summary, and we get minimum, mean, maximum, that kind of thing. Now, another thing, you might be a little lost by this. I always have to look this stuff up. I cannot do this dplyr piping without looking for help. So what I really encourage you to do, I did a really quick Google search and I said, I put in gather dplyr, and then I got into this instruction page on the internet. So here it basically tells you, you always will use gather, the data set, key, some sort of value, some sort of name that you're going to make it, a value, and then some different things. Down here in the arguments, it actually tells you what it's supposed to mean. Some of this may be not as clear as mud, but anyways, some sites are a little bit better than others with helping you understand what the language. What I often do though is I go down to the examples. Okay, I'm going to skip down here a little bit. So the iris data set is a really common data set. You can type in head iris in your computer in your R right now, and it will show you what that iris data set looks like. And then what you could do is here they're going to gather, they made mini iris a new data set with just certain rows, okay, 151 and 101 with all the columns. And then they're going to gather it together, and they wanted to do like the species, the flower, something or other, length, I guess, width, that kind of thing, and then also the measurement. So you can actually play around with this kind of thing to make it work and to change your data. So it's really a handy, fast way, believe it or not, of modifying how your data look for different analyses. So always get in there and look for examples and help on the internet if you have them. Okay, now that we have these two things, so we're going to do some quick plots to check our data. So here we're going to use ggplot. We're going to tell it we want RH, the radar hill species number data set that we made using the gather function above. That was the first of the two that we did. On the x-axis, we're going to put habitat, and on the y-axis, total species. We want a box plot. You can do geom point, but geom jitter, if there's points that are on top of each other, jitter will kind of just jitter them around so that you can actually see all of the data on your plot. Theme BW, we will typically be using theme classic in this class, but here I just have theme BW so that you can see it. Again, a good idea is to always kind of make it before you label it. So I'm going to highlight that part and see what we have. So here we can have total species on the y-axis. We have habitat on the x-axis. We have in, not, and out. And then you can see how our data are jittered. If our data were if it was just geom point instead of geom jitter, these points would be on top of each other. It wouldn't look like we had very much data. So now that we know that the plot, and see again what I did, I just highlighted the part of the code that I wanted to run, and then I hit Control Enter on my PC. I had to make sure that I didn't do the plus sign after that. You can also do like a hashtag after something, but then you have to delete it. So it's just easier to highlight as long as you don't delete your code. Okay, so now that we know that this plot is right, and we want XLab to be restoration treatment instead of habitat, for example, and we want YLab to be total number of species in the quadrat, and then on the x-axis, scale x discrete. So instead of calling these in, not, and out, we want to actually say inside restoration plot, outside restoration, and not restored. Now, notice that this is out of order, okay? Not is second. So if we just went blindly through and did this code and typed it however, we would be wrong. So I'm going to actually go ahead and fix my code. Cut it, put a comma, paste it, and then get rid of the extra comma. So let's check that again. It should be inside restoration plot, not restored, and outside of the restoration plot, correct? All right, we can go ahead and run this whole thing now, and now we actually have this labeled right. Inside, not, and out, okay? We can do the same thing, and I think I did this on all of them, so I'm going to fix this code now while I'm thinking about it. Part of what this R always puts it in these in alphabetical order, and you can change the order of things, which isn't too bad. Yep, I got to fix this cursor. But anyways, you can change that, but for our purposes, I think just putting it this way for now will be really good. So here again, we're going to make another plot with the Radar Hill Prairie number. So the number of prairie species in each of our plot. On our x-axis, we want habitat. We want prairie species on the y-axis. We want a box plot, and we want to jitter it, and then the theme. The theme BW, if you've noticed, has the lines in it. Again, not real appropriate for publication quality, but sometimes it's helpful. Here we can go ahead and be like, I don't want theme BW in this class. We should be using theme classic, and I'm going to end up having that. So again, we want restoration treatment on the x-axis, the label. We want total number of prairie species in the quadrat on the y-axis, and we want to have inside restoration plot, not restored, and outside restoration plot. We run that, and we have a decent looking box plot, sorta. Okay, so another thing that we can do is we collected data on mean LAI. So this is a good thing to look at too, because we might be interested in understanding if leaf area index differs by treatment. So here, a good idea too, sometimes people will have plus and have it continue on the same line, but I think it's a lot easier to read and troubleshoot if you always do plus, enter, and then have it on the next line. So here we're going to do RH species number, X is habitat, Y-axis is your mean LAI, we want a box plot, we want to jitter it, we want our theme. We can go ahead and check it first. Make sure it did what we wanted to. Yep, habitat is on the X, so we can put restoration treatment as our label for our x-axis and LAI on our y-axis and remake the plot. Okay, so that works. Okay, now we're going to do some hypothesis testing. So when we do hypothesis testing, again, we're making a null hypothesis of no difference or no relationship, depending on whether we have a categorical or continuous variable. This is how we get our inferential statistics. So we talked about inferential and descriptive. I'll show you descriptive statistics in a few. But first, what I like you guys to do, again, notice I put 4 hashtags here so that we can quickly go through here. If you're doing your code later on and you want to get back to the hypothesis testing so that you can kind of look at stuff, you can index it and then skip to it. I always like you to write your question out in words. So put a hashtag, your question, do groups differ in total species number? And I'm just using groups as in the habitat treatment, right? We can check, okay, so our counts, so remember this is number of species that we're looking at. Are number of species normally distributed? And if you remember from lecture last week, no, counts are never normally distributed. They're what's called a Poisson distribution, okay? So we can change this. Last week we used a linear LM as our function. This week we're going to use GLM, and we can identify the family that we're using as Poisson, family equals. We can also say family equals Gaussian, and that means normal, okay? But here again, since counts are always Poisson distributed, we're going to use that. So again, I think it's often helpful to just run my names so that I remember what variables are in my data set and what hypothesis we want to test. And this is again where it's really helpful for you to write in your notebook y tilde x. What are we testing? So on our y-axis, we might want to know the total species. On our x-axis, we might want habitat. The function is GLM, family equals Poisson. This should be in quotes, and we have to tell R where to find our data. Data are in RH species number. Now, we're going to make this an object though. So again, like I like to either name all linear models LM dot something or other, what it is. So we're doing linear model of species number, or you could go species number dot LM. So whichever way is fine, but it's always a good idea to have linear model in your name of the object so that you know what it is. So we're going to go ahead and run this line of code. It ran, we didn't get any errors, but we don't know what it is until we actually call the object. So here we're going to call summary of LM species number. And if we scroll up and we look at this output a little bit, we see this is our formula, was total species tilde habitat using the family Poisson and the data set that we use. And when we come down here, again, remember R is doing this in alphabetical order. So not compared to in, out compared to in, okay? In is not listed because it's the reference level, okay? So with restoration treatment, we have 3 levels, in, not, and out. And R will always compare these levels in alphabetical order. So not is compared to in and is significantly different. We see our z-value and our p-value here. We see that our parameter estimate is negative, so we can actually say that not is less than in. Okay, and overall we can kind of see that's LAI, but if we went back to our other plot, I can kind of come back here. Total species. So when our box plots, we can compare this to the quick and dirty box plots to our information here. And we see that, yeah, it does look like there's fewer species in the outside, the not restored section compared to the restoration plots. We can also say that out is also has less species in it than the restored plots as well. And we do see that there's a significant difference and that is less, okay? So these parameter estimates give you the direction and kind of the strength of the relationship, how much difference is there. Our z-value and our p-value are here. Okay, now notice that this information gives us in versus not and in versus out, but it doesn't give us a test between not versus out. So to do that, we actually have to do post hoc tests, okay? We can't just run it again and again and again because then we'll make a mistake by chance. One of the ways that we can do this is in library EM means. Now you should have already loaded this at the beginning of the lab, but we can call it here. If we want to know what a function does, we can always type $EM means. And when I run that line of code, it actually takes me to the help page, okay? So over here, packages and help, EM means, and it actually tells me what to do with it and what things mean. Again, a lot of times I just skip down to the examples and see what happens. So here they're doing a linear model and then they're using the EM means of whatever, okay? So skipping down to that really helps. You can also come packages, and I have a lot of packages on mine. I can go ahead and click on EM means and then click on E to get to the function that I want. So you can always do that if you're not sure the function name. Now, to get our comparisons, our post hoc contrasts, okay, we're going to make a new object called number EM mean, okay, num.em mean. We're going to make that be an object. We're going to say EM means is the function. We want it to get the contrast from the model, linear model species number, comma. We want it by habitat. Okay, this is our X value up here. So tilde habitat, comma, method equals Tukey. So this is a Tukey post hoc test. Okay, there's different post hoc tests that you can use like Bonferroni, but here we're going to use Tukey. Now I put comma, type equals, quote, response. You should run this code without type response and then compare it with the response. But basically we're telling R we want to get the marginal or conditional means on the response scale. Notice up here we use the Poisson distribution. So it would be on a different scale. Those mean, or the numbers may not mean a whole lot to us if it's not on the response scale. So if we type response, then it makes it a little bit more meaningful. We run it. We don't get an error, but we don't have anything. That's because we have to call the object. So here, if we call num.emmean, the object name, then we get to see what it is. We get to actually see the habitat, in, not, and out. We get the rate. The rate is going to be the mean. This is the marginal mean or the conditional mean based on the model. So in has a mean of 5.33 with a standard error of 0.67 and so forth. And it also has confidence intervals. So sometimes later on in the semester, we'll actually be using this information to plot our data instead of just describe by. But anyways, that's there for now. And then, well, okay, we don't have a p-value there. We like p-values, okay? We should get away from p-values, but we're not there yet. So let's go ahead and run pairs. Pairs of what? The num-em-mean that we ran up here, okay? And then what this shows you is all the contrasts. In compared to not, yes, it's a significant difference. In compared to out, yes, there's a significant difference. And then not compared to out, and yes, there's a significant difference. Now I want you to notice that these z and p values are not as strong. The p values are not as significant, I guess. And that's because they're being penalized, okay? So here I'm going to go ahead and change the size of this so hopefully we can see everything. So here we can look at in versus not, and we had a p-value of 0.0012 with our independent contrast. And when we were down here, we looked at it in the model, it's 0.00046. So it's more significant here, but again, we have to penalize for asking for more hypothesis testing. So anytime you do a Tukey's post-hoc test, it's going to be harder to detect a difference if there is one. So you'll notice that sometimes. Okay, so anyways, so what would you report? Okay, you'll be thinking about this in lab. So basically you would say something like there were more species in the restoration plots compared to the non-restored plots, and you would put probably from your full model, you would put the z value, p value, remember round to 2 significant digits, the hundredths, or you can put p less than 0.001. If you can also then say there were also more species in the restoration plots compared to the outside of the restoration plots, your z and your p-value again. You can then say that Tukey's post-hoc tests indicated that there was no difference between the non-restored and the outside of the restoration plots. And then you would put your z and your p-value, okay? All right, I kind of skipped over degrees of freedom. I'm going to scroll back up to the inferential statistics, and it tells you for the model what your degrees of freedom are, so you can always use something like that, okay? All right, then we're going to ask another question. Do groups differ in the number of prairie species? So again, we're going to remind ourselves what the names of the RH prairie numbers species data set are. We want, again, this is going to be number of species that are prairie. So it's a count, okay? So we're going to need GLM instead of LM, and we want family equals Poisson. We need to have, again, prairie species. This is why I pull this up, so that I can spell it right and capitalize it correctly. So prairie species is our Y. We want habitat on our X. So again, I can make sure, yes, it's a capital H. And then data that we want to pull it from is this RH prairie num. So I'm going to go ahead and run this model, do a summary. All right, here we see that there's no difference in the number of prairie species in compared to non-restored or in compared to the out. We can still do post-hoc tests, so we can run the EM means. We can see what that looks like. We can see the rate, and again, these are smaller because we didn't have as many prairie species, and then we can do pairs, and we can see that Tukey's post-hoc tests say that there are no differences in any of our post-hoc comparisons. So you're going to write this up similar to how I said in the last example, but this time, of course, you'll use your summary stats here, saying that we did not find a difference between the restored plots and the non-restored plots, z and p-value. And again, round to the hundredths, 2 significant digits, that would be 0.23 in this case. All right. And then also report your post-hoc tests results. Now, another question we can ask is, do the groups or the habitat treatments differ in leaf area index? So we also made that graph earlier, the box plot. So this time LAI. Okay, LAI is a continuous variable and it's a mean LAI. So we can actually make a histogram to see if it's normal. Okay, and again, we would want a bell-shaped curve. This doesn't quite look normal. It almost looks like bimodal, but we're not going to really deal with that here. We're just going to go with it for this class, okay? But again, if you were doing this for a job, you would end up wanting to maybe plot it by groups and making sure that you meet all the assumptions of the model. But here, this time, because we're going to go with a normal distribution, we're going to do an LM. We're going to do mean LAI tilde habitat, and where the data are, RH species number, okay? Because we put that in there. We could also put that in RH underscore environmental. All right, so we'll run it, we'll look at the summary, pull it up, and here we see that there is no difference between the non-restored and the restored site, no difference between the outside restored and inside the restored sites. All right. And again, you can click back to your box plot that we made earlier and see if that makes sense. We can still go ahead and do our EM means or our conditional or marginal means, and then we can look at what that is. We can get our marginal means, our standard error, that kind of thing. And then we can do pairs for the contrast to get a t-value and a p-value. Notice this time this is a t-value. Oftentimes if you have a normal distribution, you're going to have a t-value. If you have a Poisson, it should be a z-value. So always pay attention. All right. And then, yeah, if you didn't do this as response, go ahead and you can delete this part if you want, just to compare. I'm not going to do it here, but if you delete that, look at what it is, and then look at it with response and see how these numbers really differ, okay? All right. Now, I told you before that I really don't want to see box plots in your reporting, okay? So last week we used describe library psych with the function describe by. So you should have loaded it above, but if you didn't or want to be sure, you can always do that. We can call up and get the help for describe by, and it kind of again tells you X is a data frame. That's the first thing that goes in here. Group, okay, how are you grouping your data? So here we're going to do describe by what? We're going to describe the RH species number, total number of species. That's our data set. We want it grouped by habitat. So again, we have to tell it what data set it's coming from, $habitat, the variable. And we are going to use MAT for matrix equals true. And this is important. If you leave this off, then you can't plot from it. But we're going to actually make like a data set that we can plot from. We're going to call this species.descript. So spec descript for species descriptive statistics. So I know it's descriptive. Okay, we're going to run it. Then we have to actually call it so we can see what it shows us. And here on this descriptive statistics, we see that we have group 1 is a new variable name. It has in, not, and out. So this is habitat. We have our N, so we had 12 samples in each. Here is our mean. So our mean for the restored sites are 5.33 species. Our non-restored sites are 2.41 species. We have standard deviation, min, max, range, and then standard error that we will actually report. So when you go and write your results with your inferential statistics like you did before, then you want to go back and show your reader how much is the difference. So if you said that there were more species in the restored plots, you would put parentheses 5.33 plus or minus 0.5 because we're rounding up to the hundredths. So since 7 is going to make 9 go to a 0, and 10, we're going to go up to 0.50 for our standard error. compared to the non-restored site, and then you'd have parentheses, put the mean for the non-restored site for 2.42 plus or minus 0.31, a semicolon, and then your inferential statistics. So it's okay to write your sentences in parts, put your inferential statistics, but then always make sure that you go back and add in your descriptive statistics. And if you can't remember how to write this stuff and just listening to me not good enough for that, go back to our statistics lecture. I have examples of how to write these up in the stats lecture. So no excuses for not doing it. All right, plus you can always ask us. All right, now we want to actually make some figures, okay? So here, again, we're going to do a ggplot, and I can go ahead and say I want species descriptive, so I'm going to use the descriptive statistics. We need our X and our Y, and this is where it's important to come down here and know what data set you're pulling it off of. So our variable name for the habitat types is group 1 in this data set. Okay, so our X is group 1, our Y is going to be the mean in this data set. Then we're going to put theme classic. Okay, so if I do this, you kind of just get a plot. We haven't really plotted anything too much yet. I want to use geom swarm, so this actually plots the data onto our data set. Notice we don't have data in this data set that we made. But the original data are in RH species number. We're going to use the function mapping, a command, equals AES. So again, the aesthetics we want it to plot. We want habitat and total species. And I want my dots to be gray, okay, instead of black. So now I can go ahead and run these 3 lines of code. And there you can see my gray points that we put in. Okay, so that's the original data. Now we're going to go ahead and add our geom point. So from our mean, because we want the mean there, and we want the error bars. So the error bars for the mean minus the standard error. So here, our point. I'll go ahead and, I guess, run that to show you. All right, so the dark dots are our means. Now we want to add and subtract and plot the error bars on that. So we're going to tell the function geom error bar. AES, this is our aesthetics. We want Y minimum to be mean minus standard error and Y max to be mean plus the standard error. And again, this is coming from this data set, okay? Mean plus the standard error. So this is important to make sure that you're looking in these data sets to make sure that you're telling R what you want it to plot. All right, so now I can run these lines up to the plus. All right, and now I have in, not, and out, and mean. All right, so that's not bad, but now we need to actually check. So here we want number of species on the y-axis to be named, and then habitat on the x-axis. You could go ahead and change it if you wanted, like we did in the others too, but here for habitat, that will be fine. Also checking, I have this wrong again, so I'm going to go ahead. This should be fixed in yours because I'm going to save it this way, but always double check. So we want the order to be inside, not, and outside, okay? So now I'm going to run the whole thing. I'm going to recall, oops, argument 4. Oh, I left a comma here. See that? So I got an error. And it said argument 4 is empty, so it was missing something. Okay, so since I had the comma, R thought I had something else coming. All right, I'm going to rerun it. I'm going to end up calling it, and now we have this nice plot with habitat, number of species, inside, not restored, and outside. Okay, now to save it in a high enough quality so that you can use it for posters or your papers, we are going to use ggSave. So we're going to call it, I usually call it the same thing as I called the figure in the first place, or the object, but in quotes you have to put .jpeg. You can do a TIFF or something else, but JPEGs is kind of my habit and go-to. Most people can read that. Then we have to tell it what we want to plot. We want to actually save the no spec fig. What are our units? All right, I like to make a 4 by 6 with 300 dots per square inch. and or 300 dots per inch, and that's the kind of quality. So 300 is a minimum. I'm going to go ahead and save it. I didn't get an error down here, but I also didn't see what happened. So now I'm going to go ahead and go to my folder. Let's see here, field ecology, labs. I gotta go find my folder that I have this all in. And here we have it, no spec fig. I made it on 9/5/2022 at 2:30. So you can always check to see if it's there. I can open it up. And yes, you can see that we have this really nice plot, okay, or figure that we can actually use in publications. Okay, so now I'm going to leave you write code for the additional 3 figures, okay, and also to get the descriptive statistics. So you had 3 hypotheses that we did above. You need to get descriptive statistics for all 3. All right, let's describe by function, get the mean and standard error so that you can type that into your text, and you also need to make 2 more plots, okay? Have a plot or a figure for each of those hypotheses tests. All right, that's it. We'll see you in the lab. Go through this ahead of time, and then we can answer questions and help you troubleshoot when you get there. See ya. Bye.